Has this ever happened to you? You're at the very last stage of your building. You drill a mounting hole, and pop, the composite completely delaminates, ruining an inexpensive part. Or maybe you've spent 2 hours in a cloud of toxic fiberglass dust just trying to hand sand 2 tubes. So they finally slid together. Hey everyone, I'm Wellel, and I'm a materials specialist. When engineers and builders choose Filament wounds, tubes or G10F are for epoxy glass tubes. They chose them for their incredible strength, but they usually end up running into a wall of hidden processing traps. Today, in just 4 minutes, I'm going to show you the science behind why these failures happen and how you can avoid them entirely. First up, let's talk about the nightmare of drilling and cutting delamination. Most people treat fiberglass like aluminum, using a standard 118C to 135C metal twist drill bit. That is a critical mistake. Filament or wound tubes are highly anisotropic, meaning their fibers are wrapped circumferentially to give them incredible hoop and burst strength, but they're axial and the interlayer strength is surprisingly weak. When a standard drill bit forces its way through, it wedges the plies apart without a specialized, brad-appointed bits to clean are the fibers, or a tighter internal fittings, mandrel to back the cut. The tool will literally punch the back layer off the tube. The second headache is dimensional tolerance. Because of how rolled, wrapped, and filament wounded tubes are cured using external shrink tapes, their outer diameters are rarely perfect. They have ridges and resin-rich spots, often varying by over 0.5 to 5 millimeters if your design requires a tight sleeve or slide fit. You're stuck hand sanding for hours. It wastes massive labor costs and ruins the concentricity of your tube. Then comes the assembly stage, which reveals another major flaw: cracking under clamping pressure. When you bolt down a heavy metal collar or clamp onto a standard hoop wound tube, the localized radial pressure easily overcomes the unreinforced epoxy matrix, causing the tube to split lengthwise. Worse yet, many commercial vendors rush their curing cycles, leaving the resin under-cured without proper post-curing and integrated UV stabilizers. These tubes will rapidly yellow microcrack and absorb moisture when exposed to the elements or unexpected thermal spikes. And let's not forget the supply chain. Trying to get custom ID or wall thickness for apprototype? Good luck! You either deal with regional, small shops that ignore your emails, or you get slapped with massive minimum orders, quantities, and weeks of lead time. Who has the time or budget for that? We believed that engineers should have to fight their materials, so we engineered the epoxy fiberglass tube from the ground up. First, we eliminated the splitting issue by moving away from basic hoop windings. We engineered a Tri-Axial lay-up architecture 0.45, 90 by layering continuous lengths its udinal fibers into the core. We increased the axial and interlaminar shear strength by over 300%. Now, you can drill, saw, and clamp our tubes without worrying about catastrophic failure. Second, we run every single tube through a precision, centerless grinding process. No more manual sanding. We hold an outer diameter tolerance of razor thin, delivering a drop-in, slidey ready matte finished straight out of the box. Finally, our tubes underwent a rigorous full thermal post-curing cycle with built-in UV blocks, ensuring absolute structural stability up to high operating temperatures without environmental degradation. Great engineering should be held back by unreliable, hard-to-machine materials. Stop wasting hours on manual rework and scrapped parts. click the link in the description below to visit our website. We specialize in agile, small batch custom manufacturing with industry leading lead times. If you reach out to our team today, we'll set you up with a free sample kits and a Onion, one consultation with materials engineer to spec your next project. Make sure to hit that like button, subscribe, and turn on notifications, because in our next video, we rate diving deep into the exact chemistry of secondary epoxy bonding. See you next time.